Like in acid-base reactions, redox reactions can use the method of a titration to determine an unknown concentration of one of the substances. Instead of having to use a separate indicator, however, the indicator is built into the reaction because transition metals can form different colors depending on their oxidation states. So, for example, we have permanganate ion that's purple, and then when the manganese changes its oxidation state, it turns colorless. So if we didn't know the concentration of iron, we could figure it out by reacting it with the permanganate, and then when the purple color disappeared, we could measure the volumes and we can determine the concentration. There are some practical applications of redox reactions, and if you're taking biology, these might sound familiar to you. One of them is to find out iodine concentrations. You can use an oxidizing agent such as the permanganate or dichromate. So remember, permanganate would go from purple to colorless. Chromate or dichromate is orange, and then it would form the chromate 3 ion, which is a dark green color. So you do need to be aware of these colors. So again, permanganate is purple, and then the manganate ion would be clear. Dichromate is orange, and then the chromate ion would be dark green. Iodine can also be used because the iodine ion is clear, but then when it forms I2, it actually turns brown. And some of our other halogens also have colors associated with them, so make sure that you know those colors for chlorine and bromine and iodine. Another reaction would be starch and iodine. When you take starch and react it with the iodine, it forms a blue-black complex. So you could figure out how much iodine is in something by that color change that's happening with the thiosulfate. The Winkler method is another application of this. It's used to measure the dissolved oxygen content of water. So DO stands for dissolved oxygen. As pollutants increase, the dissolved oxygen tends to decrease because the oxygen is being used by bacteria. So you could look at the dissolved oxygen content of a lake or a river or the ocean and figure out how much pollution there might be. To do the Winkler method, it's actually a series of reactions, 3 reactions. So if you were trying to look for the amount of dissolved oxygen, you would have to go through this series of reactions. So first you would react it with the manganese 2 ion to form MnO2, and then the MnO2 is used to react with the iodine ion. It forms iodine, which then is used in the thiosulfate reaction of starch. And so instead of being one reaction, it's actually a series of reactions. And you can relate the reactions together by doing your mole ratios. So let's say we know how much S4O6 ion we had, and so we could do a 1-to-1 ratio, and then we can compare iodine to the manganese oxide, so we could do a 1-to-1 ratio, and then we can compare it from 2 to 1 of the oxygen, and then we know how much oxygen was in the water. So you can use this Winkler method. For this method, you just need to know what it's used for, so it's measuring the dissolved oxygen content. You need to know what happens as you add pollution. The reactions you don't really need to memorize because they would be provided for you. All right, so an example of a titration redox reaction is used for measuring alcohol levels of blood, so the alcohol content in your blood. And this is used by the police when they're pulling over drunk drivers. They do their breathalyzer, and if that gives the officer an indication that it might be a drunk driver, they're then taken to the police station and blood is drawn, and then that's how they figure out what level of alcohol is in the blood to whether or not they were driving drunk or over the legal limit. All right, so in this question, we have our alcohol, which is the C2H5OH, and I know you might not know that right now, but we will learn about that when we do organic next. So that is something that would have to be told to you for this unit, but that's the alcohol. It's reacting with dichromate and producing carbon dioxide and then that chromate ion. So if we had a 10-gram sample of blood, and then we know the volume and the concentration of the potassium dichromate, we should be able to figure out how much alcohol is in that sample of blood. So to do that, we would want to get the moles of potassium dichromate. So we're going to use our understanding of concentration, and concentration is equal to moles over volume. So if we multiply both sides by volume, then we can find our moles. Notice this is in centimeters cubed and this is in decimeters cubed, so we are going to have to move our decimal 3 places to the left. So it would be 0.00925 decimeters cubed for our volume. And we're going to multiply that by our concentration. And we would have 5.09 times 10 to the negative 4 moles of our potassium dichromate. Now, solubility rules. Anything that's with a group 1 metal is aqueous in water, no exception. So potassium here is aqueous, which is why it's not written up here in our reaction, because the reaction is showing you the net ionic reaction. So even though we were given information about potassium dichromate, we can really say that this is the chromate ion because potassium will always remain aqueous, so it's a spectator. So then we can just set up some stoichiometry. And we can go from dichromate, let's see, the coefficient is 2, to our alcohol, which has a coefficient of 1. Now what we're actually doing is trying to find the percent by mass, so we're going to take our alcohol and we are going to convert it to grams. So 1 mole, and then we'll use the molar mass, has a mass of 46.08 grams, adding those masses from the periodic table. So moles would cancel, giving us our grams. So we would have 0.0117 grams of alcohol in our blood sample. So to find the percent in the blood by mass, we would do the part, which is the alcohol part we wanted, divided by the whole mass of the blood sample, times 100. And we have an alcohol percent of 0.117%. All right, and then the second part of the question says describe that color change that would occur. So hopefully you remember that dichromate is an orange color and the chromate 3 ion is a dark green. So we would see orange going to green as our color change. Make sure that you fill out the Google form, and if you need more help with understanding titrations, I would suggest going back to your notes and looking at the acid-base titration notes that we took back in the spring. And if you didn't take those, they are on my website that you can get from the Concord High School website.